Hi everyone, welcome to This Week in Space Science. I'm Michael Baltimore, your host, and I'm here with Dr. Sean Cruzen of the Coca-Cola Space Science Center at Columbus State University here in Columbus, Georgia. Sean, welcome to the show.
Thanks, Mike. Good to be here.
You know, there's always something going on. We know that with outer space. And you know, the last couple of months there's been these asteroids and meteorites and things coming around. But there's been some interesting news on a particular planet. So I want to talk with you about that today. We've got this Higgs boson thing that we've heard about with this collider over there. We want to talk about that. And we've got the 50-year anniversary of the discovery of a quasar.
Yeah,
so I've
right.
tipped everybody off, but now we've got to go in and get some details about this. So you want to start with life on Mars, question mark?
I would love to start there.
Okay, go there. Tell us what's
so
going
the kind
on.
of interesting thing is, as we're taping the show, there were two news stories that hit basically simultaneous within about 48 hours of each other. And the first of those is a brand new set of evidence for the potential existence of life on Mars. Now, obviously science has been working toward this discovery for a number of years, over the last decade really, with all this new armada of rovers that has gone to the surface of Mars and done a variety of different sets of experiments.
Absolutely.
One of the things that has been around for a while is clear evidence of past water on the surface of Mars.
Yes.
And part of that evidence is the existence of clays in the Martian surface. Now, clays are formed in aquatic or aqueous environments. So that's how you get this material that geologists refer to as a clay. And so there are a variety of clays. They are not salty, so it looks as if this must have been in a freshwater kind of environment. That's part of some of the new discovery being announced here recently, is that these clays seem to be freshwater. But there's something involved that's much, much more interesting. And what you're seeing.
Now, I'm sorry. Yeah, let me interrupt before
Go
you
ahead.
get to this. This is a great looking picture here. Let's keep on that picture.
Okay.
But the rovers are actually gathering this data that you're talking about with
They are.
mud. Is that where? Okay, I just want to be clear about that up front.
There's some digging around
Okay.
that's going on
All right.
on the surface of Mars.
All right,
Of course,
there you go.
the Spirit and Opportunity rovers have been up there for a number of years doing that. Mars Curiosity rover, which has been doing that for just a few months now, is up there taking samples. And here you have a picture of the Mars Curiosity rover. This is actually kind of an artist's conception. So you can get an idea of what it looks like. It's about the size of a golf cart, so it helps you get just kind of a size comparison of what this thing is like. And the picture that we were showing you previously was the Curiosity rover taking a picture of itself, in a sense. So this is its camera looking down at its digging apparatus and into this little tray. And what you see inside this tray here on the Mars Curiosity rover is some of those very clays that we were just talking about, which have been drilled out of the surface of Mars and deposited inside this little tray. Now, once they're in this tray, it can be fed into the analysis portions of the Mars Curiosity rover, and that's basically up through that grate that you see there at the top, and down into a set of instruments where this soil can be analyzed. The two instruments we're going to talk most about today are the Chemistry and Mineralogy Lab, or they call it ChemMin, and then something else called the Sample Analysis at Mars system. And both of them are basically facilities to do different aspects of geochemistry. So they can take this soil sample and they can run it through a variety of chemical tests and mineralogical tests to see what this clay is made out of and what interesting or unusual substances or compounds they might find inside this clay. So that's where we're going, and this is where the new discovery has come from. It's come from the analysis of those soil samples that you were just seeing right inside that dish. Here's the interesting thing that the Mars Curiosity rover has found.
All right.
There's something that my friend Neil Garner, who's one of our educators at the Coca-Cola Space Science Center, has nicknamed CHNOPS.
Okay.
CHNOPS.
I'm not sure about that.
CHNOPS.
Okay.
So
right, where's he going with that? Yeah, we got to find that.
You may or may not find this anywhere else. It may be a Neil Garner original. I'm not really sure.
Okay.
But it's a way to help us remember what those letters stand for. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur.
All right.
Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. That's CHNOPS. Those set of elements, those are the chemical compounds from which life is formed. And so if those chemical elements are found up there in various compounds in that Martian clay, different combinations of these CHNOPS elements, we can begin to say, well, there is a very good possibility that those chemicals were deposited there because of life forms being on the surface of Mars. And guess what was found inside that Martian clay? CHNOPS, right? So carbon, hydrogen, oxygen, phosphorus, sulfur, and nitrogen. I think I left out on the first way through. But all of those life-forming compounds were found in the Martian clay. And here's a very interesting photograph right here. On the left-hand side, you're going to see a little bit of a dig into a rock through a tool called the abrasion tool. This was on the Curiosity, I'm sorry, it was on the Spirit and Opportunity rovers. So the smaller rovers, which were up there first, all they did is they kind of scraped away the surface of rocks a little bit. On the right-hand side, you're going to see a hole.
Oh, yeah.
And that hole is very different. That's from the Mars Curiosity rover, or the Mars Science Laboratory, the big rover that's up there now. It can actually dig several inches down into the Martian clay. The sample that we saw was taken from a depth of up to 2.5 inches. So it's much different than just kind of scraping the face of the rock and seeing what's underneath. This is actually drilling down into that soil, bringing that soil sample up, placing it in that analysis tray, and being able to do what a geologist might do if they were actually out there on the planet.
I'm just fascinated by the clarity on the pictures.
Yeah.
The one on the right is amazing clarity. It looked like you were standing there with a camera to take that.
Very true.
And then get that picture back from Mars, from the planet Mars, back to Earth, and that's having it on the screen today. That's the first thing that I know. But also, it dug down. It's a black hole, if you will, pardon the pun, but I guess. But it went down 2 or 3 inches to get that clay out of there, and then having all of these chemicals and components in there. So that's pretty amazing.
So the interesting part about that, and you're right about the high definition pictures, by the way.
Yeah.
So that Curiosity rover is just loaded with these cameras that can take really high resolution images of basically everything it's doing. So it's almost as if a scientist were actually standing there doing these kinds of things, him or herself, up there on the surface of Mars. And so the interesting part about that is that soil sample then with these life-bearing or these life-composing compounds or elements, is it really life? Did life somehow exist in whatever aqueous environment formed these clays and then left behind its signature with this CHNOPS set of elements? Or was there some other kind of geological process taking place on the surface of Mars that allowed for all these things to be deposited in that clay? That's unknown at this point, but it's one more very clear indication that life could potentially have existed. Now, had they dug around in that clay and they not found any of those elements, then that would be an indication that probably there was never life, at least in that particular area of Mars.
Right.
So this is a green light for the continued search for life on Mars, not a red light.
Right, and you know, there was water at one point on Mars, like you said earlier in our conversation today. Now, do we have any idea about what happened? Was there an atmosphere on Mars? Was there water at one point and the atmosphere sort of got sucked away, or something happened to it and then the water went away as well? I mean, what's the story there?
So Mars as it exists today simply could not support any kind of surface water at all. The atmosphere of Mars today is far too thin, tenuous, to be able to have liquid water on the surface. Yet there's evidence of liquid water on the surface of Mars almost everywhere in the geological record, which tells scientists that in the past on Mars, there was clearly a much thicker atmosphere at one time. And that atmosphere was able to support large bodies of liquid water deposited in various locations on the surface.
Right.
And so the concept is, well, what happened then to that atmosphere? Well, the thing you have to know about Mars is it's much smaller than the Earth. It's only about half the size of our planet Earth. Okay. And it's a lot less dense than Earth, which means overall the planet Mars has much less gravity than Earth does. Okay. And so because of that lower gravitational, what we call a surface gravity, that lower gravitational field at the surface of Mars, the planet Mars would not have been able to hold on to a vaporous atmosphere the way that the Earth has. So yes, Mars still has an atmosphere today, but it's very, very thin compared to the atmosphere of the Earth. It's only about 1% of the atmospheric pressure here on the Earth. Okay. And so despite the fact that it looks like at one time Mars had an atmosphere, it does not now. That's very largely due to its low mass. That atmosphere simply evaporated off into space over time, and now surface water cannot exist on Mars. However, the question is, does it exist below the soil?
Right.
And this is why, you know, the scientists are using Curiosity rover and other instruments to dig around in that soil and try to find evidence of not only past life on Mars, but potentially present water and present, maybe even biotic or life forms up there on the surface of Mars.
Wow, that's it's so exciting to know, and the Curiosity rover is doing its job so well. Isn't that an amazing piece of technology that allows us to go there and get those pictures back, analyze the samples on the spot, and send that information back?
It is one
tremendous.
bad Martian hot rod.
You got it.
Is. You know, imagine being a kid and thinking about going into the field of astronomy or planetary studies, and you might dream of, hey, maybe someday I could build a remote control car and drive it around on the surface of Mars. Well, that's exactly what those guys at JBL are doing right now. All the scientists at JBL, they're taking part in this mission where they are allowed to drive a car around on the surface of Mars, dig in the soil, and do a chemical analysis of an alien world. And that's tremendously exciting for that entire scientific team at the Jet Propulsion Laboratory and at NASA.
Well, I love it, and thanks for bringing in that story. We want to hear more about that and kind of keep up with it as it's bringing more information. All right, let's move to another story. The God particle has been in the news. This Higgs boson, this Higgs field. Where are we going with this story today? Because it's been out there in the news.
Well, again,
and have we found it, by the way? That's the other portion of it. Do you have a sample of that?
I don't have it with me today. However, again, as I was driving into work this morning, this is fresh stuff at the time of the recording of the show. It was just on the radio this morning that the scientists at CERN, which is the Nuclear and Particle Laboratory in Europe, announced today that their earlier data where they thought they may have found this weird particle called the Higgs boson, which has been nicknamed the God particle, that data has actually been confirmed, at least by their internal panel of scientists.
Okay.
Yes, they're claiming now it looks as if they have found what is called the God particle. And so what you're seeing right here is a massive underground machine in Europe called the Large Hadron Collider. And the Large Hadron Collider is basically an instrument for smashing subatomic particles together at speeds approaching the speed of light, controlled by tremendously strong magnetic fields that run through these giant pipes, some of which you're seeing right here in this particular photograph.
It's a great photograph.
It is a
Look
fantastic
at the size
photograph.
of that with that human guy, the guy standing on the platform there.
It absolutely gives you a sense of scale. If you look over at either the right or left-hand sides of this picture, you can see these blue stairwells that are walking up there. And so, you know, and the scientist standing in the middle of the frame. All of that gives you some perspective to the massive scale of this particular instrument. And you might think, well, why is such a gigantic instrument necessary to measure such small particles? We're talking about measuring particles that are smaller than the size of the atom. Why would that be necessary? The answer to that is they have to be able to generate magnetic fields that are strong enough to accelerate particles to near the speed of light. The other thing they need is a long enough racetrack to get that done, right? So if you were Jeff Gordon driving a NASCAR, for instance,
so just thinking about Jeff Gordon,
you would need kind of a long track to get up to top speed. Well, this particle collider is somewhat similar to that. They have to have these very long tubes in order to accelerate these particles fast enough to where they're actually approaching the speed of light. Now, why is that necessary? Well, there was this fellow named Einstein that wrote this unique poem.
Oh, yes.
And the poem went like this: E equals MC squared.
Never called it.
It's a lovely poem.
Called a poem before, but yes, I think
it's one of my favorite pieces of prose written by Albert Einstein. That equation is called the equivalence principle. The E is energy, the M is mass, and the C that gets squared, that's the speed of light, which is a very big number. And E is on one side of the equal sign, and M is on the other side. And what the equivalence principle really says is that energy and mass are kind of the same thing. They are different forms of the same quantity. Therefore, mass can be converted to energy and energy be converted to mass. That's what the equivalence principle says. So in order to explore this world of these strange, weird subatomic particles, you have to give the parent particles, in other words, the things you're going to smash into each other, you have to give them a high enough speed that their energy is high enough to be equivalent to the mass of the particle you're trying to study. So that's why that tremendously high speed is necessary. You have to achieve that energy level to be equivalent to the mass of the particle that you're trying to create in that collision. And so that's why it's necessary to have that gigantic apparatus, that big long racetrack, those extremely powerful magnetic fields to circulate these subatomic particles fast enough that when they do hit, they have so much energy that you can create a whole zoo full of subatomic particles and really study in depth their nature.
I'm a little curious about the how often they collide on this collider in CERN. I mean, is this like once every so often? Can we do it once a week? Can we start colliding things and see if we can find this this God particle? I mean, or is it once in every so often? Do you have an? I know I don't want to throw a question at you like that, but that was just occurred to me.
These are precisely the kinds of questions I'm here to evade.
There you go. There you go.
But the idea is that I'm not a particle nuclear physicist. However, I can tell you this: that once they fire up the Large Hadron Collider, it's colliding beams of particles. So it's a set of streams of particles that are smashing into each other, creating all kinds of collisions, all of which are being recorded. So as long as the Large Hadron Collider is running, it is in fact colliding streams of particles. A continuous set of collisions are taking place, and measurements of those collisions are being recorded. That's as long as they're feeding matter into that stream. So it's not simply one collision. They don't wait for two little tiny subatomic particles to hit and then draw a sketch or something like that. It's a constant stream of collisions, all of which are being recorded, all of which are being analyzed statistically, and then from those statistics, they expect to see these certain trajectories after the collision, and allows them to identify various subatomic particles.
Yeah, it's been a while since they first had the collision, and now they've really had to go back through sets of data, I would imagine, and really do the research and kind of pull this information out.
That's exactly right, and so that's the way a lot of science works. And you know, science is a very glamorous field in a lot of ways, and you know, I happen to be an astronomer, and so people get the idea that, oh wow, you get to spend all your time at observatories and exotic locations on mountaintops using telescopes. And in fact, the career of the astronomer spends very little time actually at the telescope, a lot more time back in the laboratory or in the office analyzing that data. So same is true for the Large Hadron Collider. They fire it up, they get a set of collisions, they get the data from that particular set of collisions, they take it back, and they do a very long and tedious analysis of all that data. And so it's these analyses of data that have led to the discovery of this weird thing called the God particle. And maybe we should talk a little bit about that. Yes. What is the God particle?
All right, that's a good question to begin with. Since we've discovered it now, we might as well define it in some ways.
Well, let's first start by talking about a guy named Peter Higgs.
Okay.
Peter Higgs was a theoretical physicist who first proposed a couple of decades ago the existence of this weird thing, this underlying set of fields called the Higgs fields. And the Higgs fields were a proposed set of energy that would explain why particles have mass. See, that was the real question. It's almost a philosophical question in a sense. Why do particles have mass? And moreover, why do some particles have different mass than other particles? And so Peter Higgs kind of addressed this by saying, well, maybe what we're seeing is the result of this underlying field, now called a Higgs field, and that Higgs field interacts differently with different particles, or I should say, the particles interact differently with the Higgs field.
Okay.
So for instance, you have a proton, it has a certain mass, then you have an electron, has a much, much smaller mass. The electron has a much weaker interaction with the Higgs field than the larger proton does. How can we imagine this in a little bit more clear terms?
Sure.
Well, there's a nice cartoon that I brought in today. And it's a picture of Albert Einstein at a party of physicists.
Okay.
And so here's Albert Einstein. Now, obviously, Albert Einstein would be by far the most popular scientist in the room because, after all, he is Albert Einstein. And he wrote that neat poem I told you about.
Oh, yeah, I was curious. And also, somebody's done some cartoon work here, and I'm wondering what magazine or journal, scientific journal, that you've actually pulled this from, but that's okay.
I believe this first appeared in the journal called Science.
Okay, there you go.
But this is a cartoon to help explain what a Higgs field is. When Albert Einstein tries to move through this room of physicists, he is so popular that everybody wants to talk to him. And so all of those scientists are gathered around him, which means he has a much harder time moving through this room than pretty much all those other people who are standing around the corner only talking to one person.
Yes.
Right? And so they would have a very easy time moving about the room. They would have a very low interaction with the rest of the Higgs field around them. But Albert Einstein, because he's so popular, would have a much harder time moving through this crowd of scientists.
All right.
Therefore, he would have a much higher interaction rate with that surrounding field, and moving would be a whole lot slower.
Okay.
Einstein's mass would be high, the unknown physicist's mass would be low, and that's a way to make an analogy for the
Okay,
Higgs field.
I got it. Yes, thanks. For helping
Another
us
way
with
is
this.
imagine a fish swimming through water, and imagine me swimming through water.
Okay.
The fish has very low resistance and can swim right through the water with no problem.
Right.
A barracuda, for instance, zipping through the water. Me, on the other hand, swimming, well, I have a
Yes.
higher friction rate with the water than a barracuda.
Okay.
I think it can clearly be shown.
I would like to see that contest, by the way. Daniel, think we could arrange that with a barracuda and Dr. Cruising in the swimming pool? Maybe we could test that out a little bit.
Because
get
my
some
body
data.
would have a much higher interaction with that water, it would slow me down.
Yes,
Whereas the
I
barracuda could go
understand.
zipping through.
I definitely understand
The barracuda is like a low interaction particle with a low mass,
Okay.
interacting with that Higgs field, which is like the water itself. I would be like a much more massive proton, or maybe even a boulder or something, trying
Yeah.
to move through the Higgs field with a whole lot of mass, and there would be a big difference.
Okay.
So that's what the Higgs field is. It's that underlying field. Well,
Right.
if that's what the Higgs field is, what then is the Higgs boson? Well, the Higgs boson is simply the smallest quantity that you can have of that field. And if we go back to that swimming pool analogy, we know that we can break that swimming pool down into individual droplets.
Okay.
And in fact, we can break those droplets down to individual water molecules. Yet, when you stick your finger in the water, you don't have a hole that develops in the swimming pool. It's pretty much a continuous medium. So the Higgs field is like a continuous medium, but it's made up of these little individual particles, the Higgs bosons, which are similar to the individual particles of water. That's what they found. They have found the existence of those little Higgs particles. So if they exist, that means this underlying field of the Higgs field exists, and it looks like that supports what we call the standard model of particle physics. It
Okay.
looks like that is indeed why particles have their mass. There does appear to, in fact, be a Higgs field for particles to interact with. It's not just a flight of imagination anymore. It's verified science now, as what it looks like, at least with this new data, that the Higgs particles exist, therefore the Higgs field exists. Therefore, that really is why particles have varying masses.
That is very interesting. When you talked about the Higgs field, and you got to refer to this picture right
Well,
here
this
because we need
is
to know
this
about
is a
that.
set of data from that collider. So all of these little different spirals
Right.
are how different particles of different mass fly off in that very strong magnetic field. So every particle with a different mass and a different charge will fly off through that magnetic field in a different path flight. And so all those little different spirals and different colors right there represent the existence of different particles. So it's this kind of data that the scientists of CERN were looking at, and they knew which one of those spirals to look for to find the Higgs boson.
Right.
That is the kind of data that they were looking for, and that's what led to the verification of this particular particle.
Wow, this is very interesting. I'm almost thinking about something we talked about a little while back in another show, was this dark energy, dark matter that we hypothesize that are out
Yes,
there that's
yes.
holding these galaxies together in our universe and all of those kind of things. And I'm wondering, this is almost an analogous kind of situation that they found this field where these particles are actually suspended and working in, and we have that same kind of notion with this dark matter with the universe. So
It's interesting that you brought that up, because a lot of cosmologists were watching this set of experiments very, very closely. And they were hoping for this other particle to be discovered, which they called a super Higgs.
oh,
In other words,
okay,
a particle of
interesting.
even greater influence on the rest of the particles that would help them to try to explain the existence of dark energy and dark matter, which is still very much misunderstood or not completely understood.
Right.
We see the interactions of dark energy and dark matter, but we don't know what it is. We don't have an explanation for it. So cosmologists were very much hoping that there was another particle that was going to emerge out of this data from the Large Hadron Collider that would indicate the presence of these weird particles called super Higgs bosons. They were not discovered. So the God particle, yes. The super Higgs, no. And so dark matter, dark energy, still among the mysterious realm of unexplained phenomenon in the universe. We can see they're there. We can kind of have evidence that something's going on that we don't fully understand, but we were not able to confirm at least one model for an explanation through these measurements from Large Hadron Collider.
Okay, very, very interesting stuff. We gotta keep up with this, and I assume you're going to follow this for us as they discover more information from that data set that they have out there.
I will indeed.
All right, great stuff. All right, our final story today, we got to talk about quasars. So, what are quasars, by the way, before we get too far into this? And this is an anniversary of some sort, right?
So to me, this is actually one of the most exciting. This is the most exciting story of the day. I'll have to admit.
All right,
these other great discoveries, they're
like those other
no
stories
doubt
too,
they are
but
very, very interesting. But for me personally, this is a great story, and I'll tell you why in a moment. So, 50 years ago,
yes,
there was a time when this weird object was discovered by radio astronomers. They were ultra bright, or in other words, very, very energetic radio sources out there in the universe that were discovered by these newfangled things called radio telescopes. Now, this is in the 1950s, and so radio telescopes were just coming along as an emerging technology, and they started pointing these new radio dishes at the sky and basically listening in radio waves to the universe, and they found some very intense radio sources out there. Right. Well, when they found those and located them in the sky, there was a catalog called the third Cambridge catalog of radio sources.
Right.
Optical astronomers began to look out there in the universe and try to find these correlating objects. And what they found with the locations of these radio sources, they just found these things that look like stars. And where this is a great picture, but there's a picture of one that looks just kind of like a star. And so when they found the star-like object, it just looks like any other star in the sky, except they were very, very faint. This is it right here. So this is a photograph right here of a very an object that looks like any other average star out there. So they nicknamed these things quasi-stellar radio sources.
Of course they would.
So they're quasi-stellar because they kind of look like stars, but then they're a radio source because they're these tremendous radio sources that end up on the third Cambridge catalog and things, right? So there was a big mystery. What could they be? They're putting off optical light like the star is, and they're also intense radio sources. Well, what it turns out they were actually distant galaxies that were, remember, when we're looking back in distance, the farther away we look out into the universe, we're also looking back in time. And that's because light travels at a finite speed. That was a different Einstein poem, but light travels at a finite speed. And so the further out we look, the longer it's taken that light to get here. So we're looking really back into history.
In history, yes.
And it turns out that these galaxies that are extraordinarily far away from the Earth were in a different phase of their life cycle. Inside the center of every galaxy are these crazy things called supermassive black holes. And these supermassive black holes, particularly in spiral galaxies, there was a period of time where they were simply consuming billions of tons of matter. And all of that matter, as it fell into those black holes, was literally belching out an amazing amount of energy.
Has to go somewhere.
It has to go somewhere. So the energy of gravitational infall was being released in terms of electromagnetic energy, and that light signature is what we see from these distant quasars. So if we can bring that picture back up again that shows one of these artist conceptions, we'll have a little bit better idea of what it is. It's really the center of a galaxy. And here's this is a beautiful painting of one right here.
Painting.
What you're seeing is a newly forming galaxy. It hasn't even pulled itself quite into a disk yet, but down in the core of that galaxy, you can see a lot of energetic processes going on. That's where all that matter is falling into a black hole. You see that line shooting out away from the center of that galaxy, that newly forming galaxy. That's what's called a radio jet. And so it was proposed that if these supermassive black holes existed at the cores of galaxies, they ought to have magnetic fields. And along those magnetic fields, you ought to have these giant radio jets. And we can look back at one of those actual photographs of a quasar, and we can actually see some of the radio jets right here. So here down and to the right slightly, below this object, you'll see what looks like a long line of glowing material. Mm-hmm. That's a radio jet from an actual quasar. So this, in fact, this quasar right here is a very famous quasar called 3C 273. 3C stands for the third Cambridge survey of radio objects.
All right.
273 is simply its catalog number. So
right.
which number was it? Well, it was number 273. This quasar was the one that was studied by an astronomer by the name of Martin Schmidt. at Caltech in 1963. And what Martin Schmidt did is he did a little bit of a different observation. He pointed his telescope at that very object. There's a photograph of Martin Schmidt right here.
There he is.
He pointed a telescope at that very object, and he let the light come through that telescope, then through a prism, and broke it up into a spectrum. And you know what he noticed? He noticed those fingerprints of elements that we see in a spectrum of light from stars. And there were some telltale fingerprints from this element, hydrogen, which is the most common element in the universe. And if you look at the top of this particular spectrum, this is actually the real spectrum. There's some lines labeled H beta, H gamma, and H delta, actually in reverse order, H delta, H gamma, H beta. Their actual wavelengths are listed below on a comparison spectrum, 410 nanometers, 434 nanometers, and 486 nanometers. You might notice that the strip on the top, the spectrum of 3C273, does not line up with that laboratory comparison down below. And that's because this light had been cosmologically redshifted. But not only that, astronomers at the time knew about a cosmological redshift, which is the universe expanding, so objects that are moving away, their light tends to be shifted toward the red end of the spectrum. But these lines were shifted so much that scientists simply didn't recognize them anymore. They were shifted entirely out of the part of the spectrum which they were even looking for hydrogen lines. It was Martin Schmidt that first said, hey, I'm seeing these lines, they don't line up with anything else, but they kind of look like hydrogen lines. And that means they would have to be at an extreme redshift. And that would imply that they are at an extreme distance, which was the very first indication that if that really was the case, and we were getting intense radio waves and any visible light at all from this object at an extreme distance, this thing had to be some kind of super source. Right. Literally an energy source that no scientist could explain at the time. It wasn't until a few years later where another scientist by the name of Donald Lynden Bell started investigating what would happen if matter fell into a black hole, that he began to realize that tremendous amounts of energy would be emitted. And then that lined up with the model that was discovered by Martin Schmidt. We have these tremendously distant objects that are putting off crazy amounts of energy. So it looked like then all the pieces fell together. And that was the way that we began to understand some of the most distant objects still to date that we can see in our entire universe, the mysterious quasars.
And they're giving off so much energy, we get to check them out with these.
We do indeed.
This data. All right, that is pretty amazing.
Now, I'll tell you one last.
Anything else?
Yeah,
yes.
I have one last.
I thought you had something
I have a
else.
subscript to this story.
All right, go ahead.
So here's the subscript to the story. At the time that Martin Schmidt was a faculty member at Caltech, he was mentoring graduate students, and here's a shot of him contemplating a spectrograph which he used to measure the quasar right there.
Kind of looks like a professor there.
He looks very much like a professor, even the bow tie. I'm thinking about getting one of those. Anyway, so he was mentoring some of the first wave of female astronomers, in the modern age at least, to come to Caltech and really take up the pursuit of the field of astronomy in a serious way.
Okay.
And one of those female astronomers was a woman by the name of Donna Weistrop. So Donna Weistrop was a female astronomer who got her PhD from Caltech, studied under Martin Schmidt. He was her advisor.
Okay.
She studied quantum mechanics under this guy by the name of Richard Feynman while she was there as well.
Okay.
And what the interesting thing about that is, at least for me personally, she was my advisor at the University of Nevada, Las Vegas.
Okay. All
so
right.
I have this kind of neat lineage from Martin Schmidt to Donna Weistrop to me. That does not put me in any way in Martin Schmidt's category, but I feel this kind of family connection, if you know what I'm saying.
Oh,
Scientifically speaking, to the great discoverer of the quasar, Dr. Martin Schmidt.
Oh, so. I love it. That's a great story. I'm glad you added that in there. Yeah. All right. Glad to know you, by the way.
Thank you very much. Thank you very much.
Yeah, nice lineage. All right. So we've come to the end of our show today. I want to thank you for viewing. You've been here with Dr. Sean Cruzen, the director of the Coca-Cola Space Science Center here in Columbus, Georgia, associated with Columbus State University. I'm Michael Baltimore, your host, and we hope you will continue to watch TWISS This Week in Space Science. We'll see you next time.